Today we are looking at the Russian peasant algorithm, also known as the ancient Egyptian method of multiplication. It is a simple, elegant procedure built from halving, doubling, and selective addition. I'll follow the treatment in chapter 1 of Stefanos from mathematics to generic programming, which is where this particular formulation of algorithm comes from. To get a feel for the algorithm, let us run through a concrete example. Let us multiply 41 by 59. Because 41 is an odd number, we halve it, we double 59 and add 59. Now to get the product of 20 and 118, we halve 20, we double 118, and that 59 will continue as it is. So now we have 10 into 236 plus the 59 from the above. Now to get the product of 10 and 236, we halve 10, double 236. So we have 5 into 472 plus 59. Now 5 is odd number, so we halve 5 to get 2. We double 472 and we also add 472. So 2 into 944 plus 472 plus 59. Now, which is doubling 944 will give us 1888. The 472 plus 59 will get copied. Now adding this, we get 2490. In this video, we are going to prove that the algorithm is correct. We'll do it twice. Once using a binary representation in Agda and once using piano naturals in rocq. Two different number systems and two different proof styles and one underlying idea. Let us begin with the binary version in Agda. Let us go about defining our binary data type. This type allows us to have somewhat intuitive binary representation. Let me define a few helper functions. Now we can do a few tests here. Right. However, we have a problem with our data type. Our data type allows us to have leading zeros. In a sense, I can have something like this, which is still the same, right? But this causes problem. For instance, I cannot expect that to work here, right? Because Agda does not realize that these two leading O's do not add any value, have no effect, that this number is same as what we had previously. The problem here is structural. The constructors of bin allow more than one way to write the same number. That means the syntax is not canonical. Agda does not look at the meaning of these terms, it only looks at their shape. So two different shapes that represent the same number mathematically are still treated as different values by Agda. This mismatch creates a lot of friction when we start proving things. We'll have to keep justifying to Agda that two differently shaped terms represent the same number mathematically. The issue is not with Agda but with our data type, which admits multiple representations to the same value. What we want is a binary type where each number has exactly one valid representation. Then Agda's built-in equality lines up with mathematical equality and the proofs become cleaner. The standard library provides such a canonical binary type, so let us switch to that before we start proving the Russian peasant algorithm. Binary is defined in the standard library with three constructors like our bin type. The first constructor represents 0. It does not need any arguments. The second constructor takes another binary number as input and is used to represent non-zero even numbers. The third constructor too takes a binary number as input and it is used to represent odd numbers. Let us try an example. Let us try to represent 11 under this type. 11 is an odd number, so we'll have to use the odd constructor. Now 11 is 1 plus twice of 5. 5 again is an odd constructor, is an odd number, so we'll have to use the odd number, odd constructor again. Now 5 is 1 plus twice of 2. 2 is an even number, so we'll have to use the even constructor. Now 2 is 1 twice of 1 plus 0. 0 is its own constructor. That's it. So we have 11 under this type. Like earlier, we have 4 constructors here. We used 0 once, even constructor once, and the odd constructor twice. Now let us go about defining a few functions and lemmas. In fact, all the functions that we care about are already present in the standard library except for half. We want a function that takes a binary number and returns the half of it. It's pretty simple function. Half of 0 is already 0. If the input number is of the form is built using the even constructor, that is, it is of the form 2 times 1 plus x, we know half of such a number is going to be x plus 1. And we can rely on the suck function from the library to get the result. Now, when the number is of the form, when the number is constructed using the odd constructor, that is, it is of the form 1 plus twice of x, half of it is just x. Let us go about building a few lemmas now. Let us start with our first lemma, that when x is even, double of half of x is x. That is, halving an x and doubling it is going to give us back the original x if x is even. Let us prove this by performing induction on the witness that x is even. So the witness can be either of the form even 0 or even 2. So when it is of the form even 0, we know x is equal to 0. In such a case, Agda will automatically figure it out that double of half of 0 is 0. So refl is enough here. Now in the second case, where the witness is of the form even 2 of y, what it means is that x is equal to 2 times 1 plus y, right? That is the definition of the even 2 constructor of even data type. So in such a case, we need to prove that double of half of x actually results in x. Now, because x is equal to 2 times 1 plus y, substituting x, we will get double of half of 2 times 1 plus y. From the definition of half, we know half of 2 times 1 plus y is suck y. Now, we have a lemma from the standard library where 2 times 1 plus underscore of double suck y. What it means is that for any y or for any x, double of suck of x is equal to 2 times 1 plus y. Now, but we know that this same as this is actually the x. So that's our proof for the first lemma. Now let us consider the lemma that for any two numbers x and y, half of x times double of y is the product of x and y if x is even. That is, for all x and y, even x and x is even, then half x into double y is equal to x into y. It's a simple proof. We start with half x into double y. We have a lemma from the standard library called double of x is equal to x plus x. That is, for any x, we can if calling double of, we can replace double of x by x plus x. In this case, we invoke that lemma on y. So we'll replace double of y with y plus y. Now we use the distribution law of multiplication and addition of binary numbers from the standard library. So half x into y plus y is same as half x into y plus half x into y. Now the previous function that we saw, the double of x is equal to x plus x, we use the symmetric version of it on half x into y. So because we are adding the same number twice, so it is double of that. So the result is double of half of x into y. Now there is another lemma in the standard library called double star rocq, which says that double of a into b is equal to double of a into b. Now we have seen earlier that earlier lemma that if x is even, then doubling the half of x is same as x. That lemma needed the proof that x is even. In this case, we already have that witness that x is even using in the form of even x. So we'll pass that to get x into y. That concludes our proof. Now let us do a couple of odd lemmas. So when x is odd, double of half of x plus 1 is what is when we get the x back. That is given a witness of oddness of x. Suck of double of half of x is same as x. Now we know if the witness is of the form odd 1 of y, we know y is 1 plus 2 times x. So suck of double of half of x is same as suck of double of half of 1 plus 2y. Now by the definition of half, we know that is same as y. So so the result is suck of double of y. Now we already have a lemma in the standard library called 1 plus 2 times 2 underscore of suck of double of y, which is same as 1 plus 2 of y, which is again from the witness, which is again the same as x. That proves this simple lemma. Let us prove another lemma where x is odd. So when x is odd and half of x times double of y plus y is when we get the same result as x into y. So the witness that x is odd is captured in the form of this variable odd x. So we begin with half x times double y plus y. Now we have this lemma from the standard library, double of x is equal to x plus x. So we replace double of y with y plus y. Then we apply the distribution law of multiplication and addition on the first part of the term to get half x into y plus half x into y plus y. Now the first two terms are identical. So we use a symmetric version of the lemma from the standard library, double x is equal to x plus x, to get double of the first two terms, which is double of first term, which is double of half x into y plus y. Now we have this lemma from the standard library again, double star rocq, which says double of m into n is equal to double of m into n. So that means the result is double of half of x into y plus y. Now we'll rely on addition, commutativity of addition for binary numbers to reorder this. So we end up with y plus double of half of x into y. In the second term, we rely on the commutativity of multiplication from standard library to alter again the operands of the multiplication. So we have y plus y into double of half of x. Now we know from this lemma star suck, we know y plus y star double of half of x is same as y star suck of double of half of x, suck of m plus m star n is the same as m star suck of n. So we end up with y star suck of double of half of x. Now we have earlier proved this lemma. Okay, let us first apply the commutativity to ensure that it is the other way around. Now we have earlier proved this lemma about suck of half of double of x, which is the same as x into y. So that is how we end up with x into y. Now that we have all the infrastructure in place, let us go about proving the main algorithm. However, instead of using an algorithm, we will use an inductive data type relation involving three numbers. A value of this type is evidence that the given number satisfies the Russian peasant multiplication invariant. We have three constructors that provide ways to legally build such an evidence. The first constructor, rp0, establishes that multiplying 0 by any number b yields 0. It states that 0 b0 is in the relation for any number b. The second constructor, rp_even, handles the case where a is even. If a is even and if the numbers half a and double of b and c already satisfy the Russian peasant relation, then a, b and c also satisfy it. That is, give me a proof that a is even and that halving a and doubling b preserves the result, then the original numbers must also preserve it. The third constructor handles the case where a is odd. If there is some number c prime such that half a, double b and c prime are already in the relation, then we have a, b and c in the same relation provided that c is c prime plus b. The Russian peasant data type encodes the Russian peasant multiplication algorithm as an inductive relation. Every constructor corresponds to one step of the algorithm, and the value of this type is a complete trace of the computation together with all the necessary arithmetic justifications. Now that we have encoded the Russian peasant algorithm as an inductive relation, the correctness proof almost writes itself. The data type tells us all possible ways a Russian peasant ABC proof can be constructed. So to prove correctness, we simply follow those constructors. If the relation was built using RP0, then A is 0 and C is 0, the statement becomes 0 into B equal to 0, which is true by definition. Agda reduces both to the same normal form. If the relation was built using RP even, then we know that we begin with A into B. We have earlier proved a lemma that A into B is same as half A times double B when A is even. So we pass the witness that A is even, which is captured here in the variable even underscore A. So we get half A into double B. But we already know that half A into double B is the same as equivalent to C when A is even. As in, we invoke the same algorithm, the algorithm that we are proving inductively on smaller numbers. So we end up with the final result, C. In the odd case, if A is odd, we begin with A into B. In such case, we have proved earlier a theorem that when A is odd, A into B is same as half A into double B plus B. Now, again, we invoke the inductively the algorithm on the smaller numbers A, B here, and on the first part of this term, we get C plus B, C prime plus B. But we know we captured the relation between C prime and B in the form of this witness C equals, which gives us C. The correctness proof is just a replay of the algorithm step by step. The data type guarantees that no other cases exist, and the proof follows that structure exactly. Let us now quickly see how the proof changes when we change the representation of numbers from binary to piano representation. This time we'll prove it in rocq. Let us remind ourselves how NAT is defined. 0 is a number. 0 is NAT, and successor of any NAT is a NAT. Because we are changing the definition of our number, the definition of our types as well as functions will also change. Now, the general proof structure will remain the same. We'll prove a bunch of helpful lemmas and then use those lemmas in the main proof. Now we can get to the main proof. This is simple reflexivity. Leah will be able to resolve this. Let us have an assertion here, right? Now again, let us introduce another assertion here. Yes, this should resolve that for us. That's it.